Very good morning, children. In today's part we will learn about two new phenomena of light, that is dispersion and scattering, and the factors on which dispersion and scattering depends, and the real life applications of scattering of light. Hope you enjoy this chapter learning, and question answers will be separately sent to you. Thank you. A very good morning, children. Today we are going to learn about dispersion and scattering of light. So we have already read about refraction of light through glass slab, prism and through lenses. So these are the two new phenomena of light, that is dispersion and scattering. So let's see first what is dispersion of light. Okay. First we come to the definition of dispersion of light. It is the process of splitting of white light into its 7 constituent colors when it strikes a glass prism. Okay. So when we find that when white light strikes a glass prism, then it gets broken up into its 7 constituent colors when it strikes a glass prism. Okay, this happens when a polychromatic source of light, that is a light of many different colors, combination of different colors of light, strikes a glass prism. So polychromatic in the sense we have taken here white light. Any combination of colors of light, we can also take red, blue, a mixture of red, blue, green and yellow colors of light. When they strike a glass prism, we find they get broken up or they get dispersed into their constituent colors. So when white light is broken up into its 7 constituent colors upon striking a glass prism, it is called as the process of dispersion. We can see here the breaking up of white light into its 7 constituent colors. And what are the colors? These are the colors of the rainbow that we find. It is, first one is violet. In series we have violet, indigo, blue, green, yellow, orange and red. Remember, dispersion is the phenomena of splitting up of a polychromatic source of light, which is basically here white light, into its 7 constituent colors when it strikes a glass prism. Okay, coming to the next slide. So we can see here the phenomena of dispersion when light is striking a glass prism and it is emitting out in the form of electromagnetic waves. Now because light comes out in the form, or light is received in the form of an electromagnetic wave, on striking a glass prism we can find that it breaks up into 7 constituent colors. So in this particular diagram we are seeing that light is emitting out, it is broken up into its 7 constituent colors, and we see the light radiations of different colors in the form of electromagnetic waves. Right? So what are these band of colors called as? These band of colors which are formed on a screen due to dispersion of white light, it is called as a spectrum. So here we can see the spectrum of 7 colors as we see in a rainbow. Basically here this is violet, indigo, overlapping with each other, blue, green, yellow, orange and red. So these colors of light, it is called as a spectrum here. The band of 7 colors of light which we obtain on a screen after light suffers dispersion upon striking a glass prism is called as spectrum. Now children, necessarily the spectrum may not be a pure spectrum. In case of a glass prism or in a rainbow, when we obtain a spectrum, we find it is an impure spectrum. Now what is an impure spectrum? A spectrum in which the different bands of colors do not have well defined and sharp boundaries. We find the colors are overlapping with each other, then it is called as an impure spectrum. We saw in a prism that when white light is striking a prism, this band of colors which are obtained, they are mutually overlapping with each other, and therefore it is called as an impure spectrum. We can see the colors of a rainbow also. The colors are mutually overlapping with each other, and hence it is called as a impure spectrum. Now, it is not necessary that always we will obtain an impure spectrum. A pure spectrum can also be obtained with the help of a spectrometer. Now, what's a pure spectrum? A spectrum in which the various bands of colors have sharp and well defined boundaries. and do not show overlapping is called as a pure spectrum, and it is obtained with the help of a device which is called as spectrometer. So you will find that in a pure spectrum the different bands of colors they are obtained as bands. Suppose this is violet, then we find indigo, then we find blue, then we find green. Like this we have separate bands of colors which are not mutually overlapping with each other, and hence we call this type of spectrum as a pure spectrum. Well, coming to what causes actually the dispersion of light. Now, dispersion of white light into 7 colors takes place because light of different colors have different wavelength. As we have already read that the violet color has the least wavelength and red color has the greatest wavelength, and yellow color of light is called as the median color, and its wavelength is the average of violet and red color. Now, since white light is composed of 7 different colors and each color of light has a different wavelength, therefore these colors of light, although they travel with the same speed in vacuum, but in any transparent medium like glass and water, they travel with different speed. Hence, due to difference in this speed, they bend through different angles while passing through a glass prism. So red color, having the greatest wavelength, travel with the greatest speed, and hence we find it gets deviated the least. We know angle of deviation is inversely proportional to wavelength. So since the wavelength of red is greater than the wavelength of violet, so angle of deviation of red color is less than angle of deviation for violet light. Red color has the greatest wavelength, so it travels with a faster speed. Now, how is wavelength related to speed? We have V as the product of frequency and wavelength. Now, frequency of light is constant, but since the wavelength changes, we find lambda is changing, and as lambda is changing, therefore velocity of light also changes when it strikes a different medium. Now, since red has the greatest wavelength, it travels with the maximum speed and gets deviated the least, while violet has the least wavelength, therefore it reaches the screen at the last, and therefore it gets deviated the most, because the angle of deviation is inversely proportional to wavelength. Okay, now we can see here when you draw the diagram on your notebook, we can also show the extreme colors of light like this, and we can show the dispersion through a prism. We can see here, this is a source of light here, sunlight. A small slit is kept here. Sunlight is allowed to fall on a prism. So here we have shown the extreme colors of light. This is red and this is violet, and other colors of light are in between violet and red. And this entire spectrum of this band of colors that we call, it is called as a spectrum. Okay, next one. So scientists children argued that white light is not formed of 7 colors, rather it is the prism which produces the colors. So Newton did an experiment to show that it is actually the white light which is made up of 7 colors, and it is not the prism which produces the colors. So if a prism is able to break up white light into 7 colors, then if 7 colors are allowed to fall on it, it should be able to recombine those 7 colors of light and produce white light. And therefore, we have an arrangement in which recomposition of the dispersed white light is taking place. Now, how it is being done? Recombination of the 7 colors of the dispersed white light to get white light, it is called as recomposing of the dispersed white light, and this can be done, we can see here, by placing a prism in the opposite direction. You can see here we have placed a prism in the opposite direction. This is the first one. This is called as a dispersing prism. This one is called as a recombination prism. Here white light is incident, gets broken up into 7 colors. These 7 colors of light again merge and recombine by the second prism, which is kept in an upside down manner, and finally we obtain a white light. So this entire combination is also called as an achromat combination of prisms. An achromat combination is a combination of a dispersing prism and a recombination prism, in which white light which has been dispersed can be recombined back to get back white light. Okay, So here we have shown diagrammatic view of how the prisms, one is the dispersing prism, the second one is the recombination prism, they recombine back to give rise to white light. Okay, now next come boys, so when you have studied about spectrum, now let's come what is an electromagnetic spectrum. We all know that light has dual nature, that is light has particle property as well as wave property. So James Clerk Maxwell, he showed that light is an electromagnetic disturbance in the form of waves, or light propagate in the form of waves through space, and it consists of two different components, that is electric field and magnetic field component, which travel in space in mutually perpendicular planes while traveling through space. Therefore, it is called as an electromagnetic wave, or we simply call it as an EM wave. Well, these electromagnetic radiations, they travel with the speed of light in vacuum and do not require a material medium for propagation and obey the laws of reflection and refraction. Although these electromagnetic radiations are composed of different types of waves, all of them travel with the same speed, that is 3 into 10 to the power 8 meter per second in vacuum. They do not require any material medium for the propagation and obey the laws of reflection and refraction, just like that of the visible spectrum that we see. Well, the electromagnetic spectrum is divided into two types. First one, we have the visible spectrum, that is called as the Wave-gear. We have the visible spectrum here, the Wave-gear, and the invisible spectrum consists of the gamma rays, X-rays, UV or the ultraviolet rays, infrared, microwaves and radio waves. So I have put here a diagrammatic view of how an electromagnetic wave propagates through space. You can see here there are two components here. One is this component and another is this component. Okay. Now both these components are traveling with a mutually perpendicular direction. Now one component has the magnetic field. This one is the magnetic field and it is written as vector B. While the another component which is traveling in a mutually perpendicular direction has electrical field properties and it is written as, electric field is written as E vector, because both are vector quantities. They both travel in space in mutually perpendicular directions and hence we call light as an electromagnetic wave. So if you put the electromagnetic spectrum together, we can see here children, this is the visible spectrum here. It has been highlighted separately. The visible spectrum consists basically of Wave-gear, violet, indigo, blue, green, yellow, orange, red, and then we have the invisible spectrum composed of gamma rays, X-rays, UV, infrared, microwaves and radio waves. So how to remember this one? We have first one, we remember the visible spectrum, violet, indigo, blue, green, yellow, orange, red. Then above red we have infrared, then we have microwaves and then we have radio waves. Okay, and below violet we have ultraviolet, then we have X-rays and then we have gamma rays, and all these are arranged in their increasing order of wavelength, or we can write down the decreasing order of frequency. Okay, so this part, violet, indigo, blue, green, it is called as the visible spectrum, while above red microwaves, infrared and radio waves, and below violet, X-rays and gamma rays, these are called as the invisible spectrum. Remember children, this is the technique of remembering it. All these nature of light waves has to be kept as it is. So we have to remember it in the order of the increasing wavelength. That means gamma rays has the least wavelength and minimum frequency, while radio waves has the maximum wavelength and gamma rays has the least wavelength and maximum frequency, while radio waves has the maximum wavelength and least frequency. Remember, when wavelength is increasing, there is a change or a decrease in the frequency, because we know that velocity of light is the product of frequency and wavelength. Now, because velocity is constant, now all the speed of light are moving with the same speed, that is 3 into 10 to the power 8 meter per second. So if lambda is increasing, frequency has to decrease in order to keep the speed of light constant. You will ask questions on arranging them, ultraviolet, X-rays, gamma rays, etc., either in increasing order of wavelength or decreasing order of wavelength, or increasing or decreasing order of frequency. So here is a list of the electromagnetic spectrum, in which we have enlisted what are the different types of waves, their typical sources, their examples of detector, their appropriate wavelengths, their typical uses and dangers of exposure. You can have a view of this list. The entire list is put up, and radio waves, we can use this one. You may not remember these two. All these three are important. Radio waves, the typical sources, examples of detector, how it can be detected, wavelength, typical sources, and dangers of if you get overexposed to these rays, then how we can save ourselves from these rays. This list is very important because questions come on based on that wavelength. You will be asked questions in which the wavelength ranges will be given, and you will be asked to identify the waves and write two of its properties or its detector, and what happens when we are exposed too much of these rays and what the typical uses. Okay, well, two important things to be noted down here, boys, that ultraviolet, especially ultraviolet and infrared, make sure you study these two properties of waves, etc., and all those things properly. Ultraviolet rays cannot be seen with a glass prism, but it can be easily seen through a quartz prism. Okay, ultraviolet rays do not get absorbed by quartz, therefore it can be easily seen through a quartz prism, while infrared rays, because they get absorbed by a normal glass prism, they are not viewed by a normal glass prism, but they can be viewed by easily using a rock salt prism. Okay, infrared rays can be easily detected by a blackened bulb thermometer, or we can also use a thermopile because of its heating effect. And UV rays, especially, either we can use a photographic film, or we can also use a silver chloride solution. Silver chloride solution you will find when it is moved from the red end towards the violet end. First the silver chloride solution is white, then it turns blue, and finally it turns black. That shows the presence of ultraviolet rays. So whenever detector is asked, make sure you write about these two detectors, especially UV rays, the silver chloride solution turning blackness, or the silver chloride solution turns black on exposure to UV rays, and ultraviolet rays can be easily detected by a thermopile and a blackened bulb thermometer. Make sure you remember these wavelengths also, because we do have questions based on their wavelength. And next, coming to the what is meant by scattering of light. Okay, the next phenomena of light is scattering of light. Now, scattering is the process of absorption and then re-emission of light energy. The air molecules of size smaller than the wavelength of incident light energy absorb the energy of the incident light and then re-emit it without any change in its wavelength. Remember, scattering is different from dispersion and refraction. It is simply the process of absorption of light energy by particles like air molecules, dust, etc., and then finally they re-emit these wavelengths, different wavelengths of light, without undergoing any change in the wavelength. So we can simply define scattering as the process of absorption of light energy and then re-emitting of light energy without any change in its wavelength. However, there may be a changes in the energy of the light wave. Hence, scattering of light is not the same for all wavelengths of incident light. So what are the factors on which scattering depends? First one, children, we have wavelength. It is inversely proportional to the fourth power of the wavelength. So we can write down intensity of scattering is inversely proportional to lambda to the power 4. That means if the wavelength of light rays is more, intensity of scattering is less. Therefore, red light. We all know lambda of red is greater than lambda of violet. Red color has the greatest wavelength in comparison to violet light. Therefore, intensity of scattering of red light is much less in comparison to intensity of scattering of violet light. And second factor is the size of the particles. So please have attention over here. The smaller particles like dust and water vapor, they scatter light of shorter wavelength. Smaller is the size of the particle, scattering is of also shorter wavelength like violet, indigo and blue. Why? The larger particles like we have water particles, ice crystals, snowflakes, they scatter light of larger wavelength like yellow, orange and red. So, smaller particles scatter light of shorter wavelength like violet, indigo, blue, and larger particles like we have water molecules suspended in the sky in the form of clouds, ice flakes, ice crystals, they scatter light of larger wavelength like orange and red. So scattering is basically of two types. We have Compton scattering and we have Rayleigh scattering of light from air molecules. So here is a pictorial representation of how sunlight gets scattered by the dust and water molecules present in the clouds, and you can see here sunlight is getting absorbed and therefore finally it is getting re-emitted with the same wavelength in different directions, and this phenomena particularly we call it as scattering of light. Now what are the some effects or simple effects of scattering of light? The first one, children, we have the blue color of the sky. The magnificent, majestic blue color of the sky is also due to scattering of light by the dust particles present in the air, which due to their smaller size scatter light of shorter wavelength. We know air is completely filled with dust particles which are very small in size, and therefore they scatter light of shorter wavelength like violet, indigo and blue. Now because of scattering of these colors of light, the sky appears blue in color. But if there is no air molecules and dust particles, we will find the sky looks absolutely black. So if the persons are flying at very higher altitudes, for example in an aeroplane, or for example to an astronaut in space, if he is in the moon and he looks at the space, he will find the sky looks completely black because of the absence of dust particles in space, because of which no scattering takes place. So no scattering of light, no dust particles, no scattering of light, and therefore the sky looks completely black to astronauts, to cosmonauts in space, and to persons who are flying at higher altitudes. Okay? The next phenomena we have the white color of the clouds. So you all have seen the white color of the clouds. I think these are called as cumulus clouds, isn't it? So these cumulus clouds, these are not rain-bearing clouds. We find they are completely white in color, and because the clouds are nearer to the earth's surface containing dust particles and water molecules, and these dust particles and water molecules are bigger in size, and their bigger in size and the diameter is quite more than the wavelength of the light used. Hence the dust particles and ice present in this cloud, they scatter all the colors of incident light to the same extent, and hence we find the clouds appear white. Remember, the clouds are very near to the earth's surface, therefore they scatter almost all the colors of light. So when all the colors get scattered to an equal extent, therefore the clouds appear to us as white. Similarly, we must have seen the danger signals are in the traffic that we use. The danger signals are usually red in color. Now what's the reason? In the visible spectrum, boys, the red color of light has the greatest wavelength. We all know red has the greatest wavelength, and intensity of scattering is inversely proportional to lambda to the power 4. Now because red has the greatest wavelength, therefore it gets dispersed the least, and hence intensity of scattering is also very less. So red can travel as a unidirectional beam to a larger distance, and it is visible to the people from a larger distance as it gets scattered the least. So red can be seen also from a greater distance, and therefore we find the danger signals are red in color. Similarly, the red color of the sunrise and sunset, we must have seen the red color of the sunrise and sunset. So here are two diagrams or two images which shows the red color of the sun during sunrise and sunset. You all must have seen. Now let's know the reason why the sun appears to us as red or yellow, orange, red in color. The sky also appears red in color. See, during sunrise and sunset, we all know, children, that the distance of the earth and the sun keeps on changing because of the elliptical path of the earth. So at the time of sunrise and sunset, light has to travel a greater distance through the atmosphere to the observer in comparison to midday. Now since blue light is of shorter wavelength, it is scattered more and is lost completely to the atmosphere. For example, children, if this is the sun, if you consider, and this is an observer on the earth. So all the colors are coming blue light and this is red light. See, blue light gets scattered to such an extent because its wavelength is less, it is almost lost in the atmosphere somewhere, doesn't reaches the observer. But red color of light, now because its wavelength is more, its intensity of scattering is least, and therefore it reaches the observer's eye, and therefore we find the red color of the sun during sunrise and sunset. And that is basically because wavelength of red is more, so intensity of scattering is least. Similarly, children, we have the blue color of the smoke. This pictorial representation, especially of the blue color of the smoke seen in Florida. So here we find the smoke coming out from chimneys, especially on a very cold day, on an icy day where we have a large amount of dewdrops present in the atmosphere. On a foggy day, it appears to be especially blue in color. And this is because the smoke contains, we find, SPM, which are quite smaller in size, suspended particulate matter, which are quite smaller in size, and hence they scatter light of shorter wavelength like violet and blue. Hence we find the smoke from a distance, especially in a foggy day or on a misty day, appears to be blue in color. Okay, similarly we have some other phenomena of scattering of light, like for example, we have our school buses, they are painted yellow because we know yellow has a greater wavelength in comparison to violet and blue, and therefore they can be seen from a longer distance. Similarly, hills, from a distance they appear to be blue because the hills, they contain a lot of dust particles and water vapor condensed near to their surface because of the cooler atmosphere, and hence they scatter light of shorter wavelength like violet, indigo and blue. Therefore the distant hills also appear blue in color. Okay, thank you so much. I hope you have understood the scattering and dispersion of light, and this completes your light chapter. Thank you so much.